So my name is Heather Versillo, and I'm with Test Oil. I am a CLS with Test Oil. I'm in the marketing department nowadays. I've been here for about 10 years, and I'll be the host of the webinar. So if you do have any questions, comments, concerns throughout the webinar, please feel free to post them in the question section. I'll be able to help you out while Evan is presenting. On that note, I would like to formally introduce Evan for today's webinar on optimizing contamination control and understanding particle counts. So Evan has very deep experience in the fluid analysis industry, and he's been with Test Oil for many years now at this point. He works with many of our customers to train them in a variety of fields that include lubrication fundamentals, contamination control, condition monitoring, RCM, MEA, and used oil analysis. Training is often geared towards the CLS and OMA1 certifications from the Society of Tribologists and Lubrication Engineers, as well as the MLA and MLT certifications, which are from the International Council for Machinery Lubrication. Evan is also a certified lubrication specialist, and he also holds titles for OMA, MLT, and MLA2 certifications. His primary professional achievements include significant contributions to STLE, such as being named the editor of TLT in 2009, and he still serves in that capacity, as well as being nominated for STLE's prestigious board of directors. Evan has also been a key member of STLE for over 20 years at this point and has donated his time to serve as the chair of the Alberta, Canada section for 8 years. And he's also an instructor of the condition monitoring course that you might see at the STLE annual meetings. He's also served as the editor of the STLE Alberta section's Basic Handbook of Lubrication, the 3rd edition. And he is a contributing editor for the STLE/CRC's Handbook of Lubrication and Tribology Volume 2, Theory and Design. And Evan also volunteers on 15 various ASTM committees, which allows him to help vote on updates to various test methods. At Test Oil, Evan's customer service objective is to offer remarkable assistance in every possible way in order to ensure that our customers are satisfied. And to that end, Evan leverages his outstanding industry credentials at Test Oil every day, and I think you guys will really getting a lot out of this. And just to double check, if everyone can hear me, can you please use the raise hand function to ensure that the audio is continuing to come in loud and clear for you? Perfect, I'm seeing a number of hands there, wonderful. All right, without further ado, Evan, I'll let you take it away.
Great, thank you, Heather. So yes, this presentation is part of a series. There's 3 parts to this series, and essentially the 3 sections are going to go over 5 steps. So this is kind of a cradle to grave handling of lubricants overview is what we'll be discussing. But step 1 begins with taking delivery of your new oil. And one of the key things about delivery of new oil is that we have to set a target cleanliness for how clean we want it to be. And one of the parts of that is we have to understand that new oil simply is not that clean. Now, what's going to be covered in some of the other parts is we'll talk about taking that delivery and storing it. And when we store it, we have opportunities to clean the lubricant, perhaps, but we should also take steps to prevent it from getting any dirtier. The same can be said once we start dispensing it. When we're handling it and taking it out into the field, we need to worry about keeping it clean, and maybe we can have opportunities for cleaning it up a little bit more. The next part after that, the last part, we will discuss what we do once the oil is in the machine. So at this point, we need to talk about exclusion. How do we prevent contamination? So that's pretty much a focus on breather technologies. And the last part being, is there any conditioning we can do? Can we remove particulate? Can we remove water? So we're going to tie right back to this original target cleanliness that we set in this part of the series. So like I said, what we're going to talk about today really is just focused on the first step. We need to understand how clean is new oil, and short version is not very clean, not clean enough anyways, and we need to set a target cleanliness. Now, before I get too far into any presentation, I always like to cover off any definitions you might need to know to keep up with terms that I'm using, and pretty much the only one that's going to affect this presentation is the term micron. You need to be clear what a micron is. It's a micrometer, or a millionth of a meter. To put it into a different perspective, it's about 0.04 thou of an inch. It's a very, very small measurement, and to help you see it in sort of a relative fashion, think of it this way. The thickness of a human hair is about 80 microns. Take that in half to 40 microns, and that's considered approximately the lower limit of human eye detection. So the unaided eye, basically dark particle on a white surface, could you even see it? Could you tell that it's there? Where I'd like to focus your attention, though, is on the two examples of blood cells, white blood cells and red blood cells. Look at those two measurements, 25 microns for white and 8 for red. Now, at some point in your life, I know we've all done this, we've all nicked our fingers or cut them, somehow we've ended up with blood on our hands. And you've probably looked at that blood and remarked to yourself that it was red. Never once in your life did you look at your blood and say, wow, it's polka dotted, right? Even though the white blood cells are significantly larger than the red blood cells, because you can't see the individual particles, you cannot detect the white blood cells among the red blood cells. Because there's so many more red blood cells than there are white blood cells, in the end, you just decide it's red. So keep those two measurements in mind in terms of how big these particles really are. They're very, very small. You cannot see them with the human eye. And this leads us to a question that is often asked of any lubricated system, and that is, what is the most damaging size particle? At what point should you be concerned about particle size? Well, there's a quote from an excellent SAE technical paper, and it suggests that the critical particle size that you should control is between 2 and 22 microns. Now, the question is that good enough? What end of the spectrum should I be at? Just really, where should I focus my energies? What particles should I be most concerned about? And I think the easiest way to understand what particle size is the most damaging and therefore the one most in need of controlling is to look at something that's referred to as the Macpherson curve. Now, the Macpherson curve was a study done using different levels of filtration and seeing how much it would affect bearing life. Now, if you start on the far right of this graphic here and look at 40 microns, again, reminding you that's the smallest particle you could see with the naked eye, it would suggest that if we filtered down to 40 microns on this particular set of bearings that was used, we could achieve about 2 million cycles. Now, if we reduce the filtration to 25 microns, you can see there is a small increase. Now, I say small, even though it's actually quite significant. It's about a 50% boost in bearing life, but it's small relative to the whole graphic. So 25 microns, we start to see an improvement, sure, but what happens when we get all the way down to 8 microns? As you can see, once you filter down to 8 microns, there's another substantial improvement if you're thinking along the lines of 50% being pretty substantial. But relatively speaking, we're only just getting started. Once you go below 8 microns, all of a sudden the bearing life rises exponentially. We can get in the tune of about a 6 times life extension by filtering all the way down from 8 microns to 3 microns. But what you'll notice, though, is after you filter much below about 3 microns, when you filter to 1 micron, you really don't continue to see that trend. It actually kind of levels off. And so this leads us to wonder, why is there this relationship? Why is the curve shaped this way? How come there's such a big impact in this essentially about 1 to 5 micron range, but beyond that, it's not really focusing a lot of energy towards an improvement? So the 2 to 22 comment is kind of truthful because it addresses part of this curve, but really that upper end between 8 and 25 microns, there's not as much improvement as there is below 8. And I think the other quote I can show you that does a better job explaining is this one here from STLE. It says the critical particle size that must be controlled is between 1 and 5 microns, kind of what I just highlighted on the graphic there. And that's because it's relating to something within the lubricated system. Now, if you look at this cross-section of a shaft inside of a bearing, you can start to understand how they arrived at those numbers 1 and 5. Because ultimately, really, the answer to the question of what is the most damaging size particle is simply a clearance size particle. Any particle larger than clearance will not get in between the machine parts and will not cause any damage. Any particle substantially smaller than the clearances will go through the system without touching anything, not certainly in a way that's going to be contacting and wearing. But particles that are at or near a clearance size will cause damage, and therefore those are the ones we most need to concentrate on. And so that 1 to 5 comment is a bit better than the 2 to 22. And just to show you what I mean by this, take a look at this chart here of dynamic clearances common in many different machine parts, and you will see that 1 to 5 range encompasses most of this list. 2 to 22 might get a little bit more of it, but ultimately most clearances are under that 5 micron value. So you can start to appreciate why we have to worry about particles in such small sizes, because it relates to the clearances in the machinery. And these are particles, again, to say we can't see, we can't feel. Now, just to show you another quick study, interesting to help us, appreciate why we worry about small particles so much. This is a study by Dr. Rabinowitz, who's known for doing quite a few studies in the field of friction and wear and how much they cost us or cause us to lose. And so this study was focused primarily on failures. Now, he didn't choose the word failure to represent this. He just called it a loss of usefulness, which is kind of along the lines of the Nolan and Heap definitions of failures. It simply means it doesn't work the way you want it to work. So when he described what was the most common cause for this loss of usefulness, he said it was surface deterioration. Now, you might wonder what that is, and that's just a really fancy way of saying wear. And you go, why wouldn't you just call it wear? It's because he was trying to reserve the word wear to distinguish physical wear from chemical wear. Because as you can see as we move to the right, there is some that can be attributed to chemical wear, corrosion as an example, but most of it is physical. And of the physical wear, he said most of it falls under adhesive wear and abrasive wear. And abrasive wear, he said, mostly came from 3-body abrasive wear rather than 2-body abrasive wear. Now, 2-body abrasive wear is when 2 surfaces rub against each other and one wins and one loses, kind of like sandpaper and wood. 3-body abrasive wear, on the other hand, is when 2 surfaces come into close proximity with each other, but there is a third body, a particle as an example, in between the 2. And in this case, the particle wins and both surfaces lose. So that's right up there with those clearance-sized particles. So as you can see, the largest slice of it, at least second largest slice of the largest slice of the largest slice causing a loss of usefulness has something to do with particulate. And one more quick study to show you, this is another one done with at least some financial figures behind it, but it shows you the most predominant source of loss is due to particulate. If you look at abrasive being the largest slice of the pie here, but you can combine that with adhesive and erosive, shows you that 82% of this pie here has something to do with particulate. So this is why we're so concerned about how clean oil is and how clean it should be, because we need to know where we're starting from and we need to know how clean we want it in operation and where we must maintain it, and that will hopefully provide us with the longest equipment life and the least losses over the time of usage. So with that, we should discuss, where does this particulate come from? And essentially, the particulate can come from about 3 different sources, broadly speaking. We have what we would say is ingressed particulate, so stuff we draw from the outside into the machine. We have stuff that's generated on the inside, and we have stuff that's even built into the system or our processes. So to give you a bit more of an explanation of these, let me show you some examples. So when we say built in, we either mean built into what we're doing, built into the procedures that we follow, built into the tasks that we perform. So things like a dirty oil container, a dirty funnel, or just even a contaminated lube source are built in contaminants because we're just going to end up putting them into the system as we go about routine tasks. However, the word built in also means quite literally built into the machine. So as we commission, install, or even construct a machine, when pieces are being put together, sometimes particulate is generated through either threading of pipe, welding of materials, just general assembly. Sometimes it's where things were stored prior to assembly. Lots of different reasons that you can have contributing particulate into a machine. When we start thinking about other sources, though, we start discussing ones that are related to being on the outside of the machine at first and then working their way to the inside, so what we call ingressing into the machine. And many of those have something to do with the environment near where the machine is operating, and some of those may be process related. So if we're crushing, grinding, milling anything as part of what we do with that machine, then we're creating particulate outside that machine, and some of that may end up being drawn to the inside. But even if we're operating what we consider to be a relatively clean environment, because nothing is happening of any great consequence outside of the machine, just general airborne particulate and humidity can be drawn into the machine And of course, this can happen through any means necessary, any opening into the system. So that could be something as simple as a fill cap or a breather or a dipstick, even things like big tank covers and inspection covers. Last but not least, though, when we say that there are internally generated wear particles or particulate being created, those tend to fall into either, like I said, wear or some other mechanism. So when we say wear, generally what we mean is machine wear, metal-to-metal contact, and there's a variety of wear mechanisms that are listed there on the left. But now down near the bottom, you'll see a few extras in there that aren't necessarily directly related to wear, but may be related to some of the components we install to help minimize some of these particulate themselves. So things like seals are meant to exclude some of those ingress particulate, but as they wear, they may contribute their own particulate. Things like filters and hoses are built of materials that if the filter or the hose degrades or fails in any way, it may shed its own particulate, never mind other particulate that's already been in the system. The other form of internally generated particulate, though, is the less obvious one, the one that has nothing to do with machine wear and has more to do with lubricant degradation. So sometimes we see particulate formed as a fallout from how the lubricant is degrading or otherwise reacting. And that can come from a variety of mechanisms, but oxidation being the primary one that's most common in most systems and will occur over time, regardless of best efforts. So when particles are created through oxidation, they can occur a few different ways. The primary way that many of us may be familiar with is what we call the generation of insolubles. Now, that's not a term most of us use when we describe it, because insolubles is not something we necessarily care that much about until such time as they plate out. When the insolubles plate out on metal surfaces, we give them new names that we generally recognize quite quickly. Things like varnish, gum, tar, lacquer. So these tend to be soft particulate that don't cause any machine damage until such time as they plate out, and then they start to insulate and otherwise can help cause parts to either stop moving or have a high restriction of movement. Another form of particulate that's created during degradation is carbon particles. As you know, oils are generally hydrocarbon based, and sometimes through reactions we strip off all the hydrogens and we're left with the carbons. Those carbons can take on different forms. Some of it may be in a form that's kind of like a soot or candle black. It can be created through microdieseling or electrostatic spark discharge, two different phenomena that can occur either because of air contamination leading to microdieseling, or restrictions of flow can lead to electrostatic spark discharge. Another form of carbon, though, can become a much harder coal-like deposit, and that's called coke, and that generally occurs under high thermal event activity. So that could be something as simple as poor cooling in a system, or something much more aggressive, like a slightly out of control heating element within a system. But anyways, we know that particulate can come from a multitude of sources, that we have almost an endless supply of where it can come from or how it can be created. So therefore, we need to start off with the right frame of mind. We need to understand how clean is this oil to begin with and how clean should it be going forward. So with that, with the 5-step program, I'll begin with step 1. That's the only step we'll cover with this one. Like I said, the other ones will be covered in the following series. So how clean is new oil? Well, honestly speaking, new oil is not clean oil. And just to show you an example of how we know this to be true, here's a published standard for the required cleanliness for, and this is specific to gearboxes, but is one of the most widely cited standards out there, simply because it's one of the few that's published along these lines. If you read this standard and start seeing what it has to say about the acceptable limit for cleanliness, you can see it here. It says it just has to be free of visible or suspended material. Remember, your lower limit of detection is around 40 microns, so you're not seeing the most damaging size particles. If this is acceptance criteria for new oil delivery, right? Take a sample, look at it in a clear vessel. If you can't see anything in it, good to go. That's not a very good standard. And that's a bare minimum, and it's a very low bar minimum to consider. Now, one of the other standards that exists has a bit more to say about this, but still is not really any better, and in fact could be construed to be worse. API 614 is a standard that's used in industry for people who are either installing or commissioning or recommissioning a piece of equipment. And during this procedure, it would suggest that as the machine is near ready for operation, that one of the last things you do prior to filling it with the lubricant is to perform a flush. Now, this is a good piece of advice, and I certainly wouldn't say anything negative about the standard at this point. However, as it describes the flush, I lose confidence in this standard quite quickly. To begin with, it says the flush should be of a duration of 1 hour. Well, if any of you have any experience with flushing, you'll know that 1 hour is nowhere near enough time to flush even some of the smaller systems. It can take days to flush a larger system. So 1 hour is definitely undercutting the ability to get rid of most of the contamination inside of a system, regardless of its size. But then it suggests that this 1 hour of flush is done at the design flow rate, meaning using the onboard pumps that may be equipped with the system. Well, if you know anything about onboard lubricant flow, you may know that this is fairly low flow. It's not considered terribly high velocity. So that's why I'm suggesting is likely a laminar flow rate. Now, if you don't know what that term is, I'll describe it on the next slide. However, just understand right now that that is a very low flow rate and it does not help us with the cleaning process. The other thing though that it says is though we're flushing it for 1 hour and doing it at design flow rate, all we need to achieve are clean 100 mesh micron screens, or 100 mesh, screens. To work that out into microns, I've saved you that little note there at the bottom and it says it's 149 micron holes. So keep that in mind. I mean, it's a little bit better than a screen door, but it's not substantially better. It's definitely not removing particles that are damaging. So when you read through the standard, it says at the conclusion of this 1 hour flush at design flow rate, trying to yield these clean screens, that you've installed 2 to 6 of these screens throughout the system. Now, there's no guidance as to where to install these screens, whether before or after critical pieces of machinery. It simply says you install them as the inspector sees fit. So you can certainly skew this if you want to, but let's assume they've even installed them in decent locations. The point is, after an hour of flowing the lubricant at this low flow rate, you pull the screens, you check them, and all you're doing is you're checking them with your eye and with your fingers. And as long as you don't see or feel anything, you consider the system to be clean. Well, the only thing you're going to see on that screen are particles greater than 149 microns, which at this point you probably shouldn't even care about because they'll probably settle out in the system. And if you can feel the particles, they're probably not damaging. So this standard essentially misses all the important things that you'd like to see as part of that flush. Now, why I was harping on the flow rate, just to give those who don't know the terms a bit of an explanation here. When we describe flow, there's a certain equation that you can use called the Reynolds equation, and it takes into account certain factors which you can see listed here. But long story short, when you do the calculation, what you're trying to determine is the flow what we consider to be laminar, meaning a very smooth stream, or turbulent, meaning, of course, that there's turbulence within the fluid. And the point of doing a flush is that you want turbulence. You want the ability to really try and pick up the particles, suspend them in the fluid, and bring them towards some other end of the system, right? Towards a filter, towards a reservoir, to be able to get them out of the critical areas of the lubrication loop. So when we do laminar flow, this doesn't generally pick up much. It barely pushes them. So you're not likely to get a whole lot of movement on any particles that are contained within the piping or the coolers or the reservoirs or whatever else is connected to the lubrication system. So as you can see, we have a standard that doesn't purport to provide very clean oil, and we've got another standard that doesn't really give us a clean, good, foot to start off from during commissioning. So knowing we have these things working against us, or not, certainly not with us, we have to come to this understanding, well, just how clean should it be, right? We're kind of on our own here, so we need to go with our own sort of mentality and decision making and say, we need to decide how clean is clean enough for our system. So what I always like to point out with people is there's no point knowing how clean it should be if you don't know how clean you're starting with. And new oil, generally speaking, if you go with just about anybody's products in any type of container, so quarts, pails, drums, totes, bulk, doesn't really matter, steel, plastic, you name it. New oil has an approximate ISO cleanliness of 2019-16 if you're familiar with ISO codes. And my point about 2019-16, and I'll always say this, give or take a code, 2019-16 is probably about 8 times dirtier than the highest OEM recommended cleanliness for an in-service lubricant. So I'm saying your new oil doesn't even meet OEM requirements. And people often get quite perturbed when they hear that statement. And I'm not attacking any particular lubricant suppliers. They're all about the same when it comes to cleanliness anyways. And people get very upset and say, why is the fluid not meeting OEM guidelines? And the point is that there's kind of two sides to this story. One is, did the lubricant supplier, did the lubricant manufacturer clean the fluid up for you? And people hearing that it doesn't meet the required OEM cleanliness would suppose that no, they haven't. When in fact they actually have. Let's give them credit where credit is due. They took this oil out of the ground. They removed, 99 point whatever percent of the dirt that was there. They left behind a little bit. So they have actually removed a significant amount of the contaminants that were in that oil to begin with. Now you're questioning then, why did they leave behind that little bit? Well, the point is, say they removed it. Say they actually did clean up your oil to the point where it could meet any OEM requirement going in. Their logic is twofold. One is that you would probably contaminate it through storage and handling practices and bring it back up to this level anyway. And two, the onboard filtration system will bring it into check. Now, like I said, people have sort of two, schools of thought when it comes to hearing this. It's not clean enough. So now that you understand maybe why it's not clean enough, the other school of thought is, why are they leaving it up to me? Why are they leaving it up to my system filtration to do this? And it's because, generally speaking, your system filtration should be capable of handling it and bringing it within check in a short period of time. And this isn't considered to be much of a burden. So it's not to say it's the end of the world and that nobody's doing things right, but we just need to realize that every time we add new oil, we're adding in oil that is likely more contaminated than the oil that's already there. And we need to appreciate this so that maybe we understand, why do we see a spike after an oil change? Why do we see a spike after a top up? It's because new oil is not clean. Once it's running in the system under filtration, it will become cleaner than it was when you originally took hold of it. Now, this value can range from anywhere from 8 times up to, as you can see here, 32 times. And you're wondering, really, that much dirtier? Is that truthful? Is that real? Yes, and I'll show you why in a second, but let me address something else. I know frequently from giving this presentation that as soon as I say 2019-16, there are some people that will understand exactly what I mean by that, and there will be others who go, I don't know what you're talking about. I don't understand those codes, or I understand the code from a certain perspective, but I don't really know what that means. So let me explain ISO coding for a second here so we can all get onto the same page so we can understand the statement of 2019-16 a bit clearer. Now, what you need to know about particle counting is when we count particles in your oil, we're reporting this as the number of particles per milliliter. And a lot of people wonder, how big is a milliliter? Well, it's about a cubic centimeter in volume. And you go, what's a cubic centimeter? Look at the tip of your pinky. It's about the volume of the pinky from the last knuckle. It's not very much fluid. It's a very, very small volume of fluid, and we are counting hundreds, if not thousands, maybe even 100,000 particles in that volume of fluid. And that leads people to wonder, well, is it a lot or is it a little? Now, bear in mind, the size of these particles that we're counting fall into 3 distinct categories that are used for the ISO coding system. We're counting the particles greater than 4 microns, greater than 6 microns, and greater than 14 microns. Now, what I'm hoping you see with that pattern there is that all of them are greater than, meaning that every particle I count as being greater than 14 microns, I will count again as greater than 6, and all of those particles I will count again as being greater than 4. So to that end, the greater than 4 micron particle count will always be the highest of the 3 values, simply because it's the most inclusive range. The greater than 14 will be the smallest of the 3 values. And when we report the particle count to you, we report them in that order of 4, 6, and 14 microns. But then what we do to simplify the reading of a report with a particle count on them, ISO provides us with a coding system to code these results. And this is where I think people really start to get lost. So let me show you the ISO coding system here real quick, and maybe we'll understand it a bit better. So if you look here, the table on the left is the set of ISO codes and the associated ranges with each code. I'll go through that in a second. Over to the right are 2 examples of a particle count, and I will go over the top example. I don't need to go through 2. I think you'll catch it on the first one here. So looking at this ISO chart here, take a look at the 5th row from the bottom where it says ISO code of 10. Any particle count between 5 and 10 particles per milliliter is given a code of 10. Now go up a row and you'll see an ISO code of 11 is between 10 and 20 particles. Go up to an ISO code of 12, the next row up, and you'll see it's between 20 and 40 particles. What most people recognize quite quickly is every time you go up a code, it doubles. Now, not only does it double in value, but here's the part some people miss. It also doubles in range, meaning the difference between the high and low value of that range, it's twice as far apart. Right, an ISO code of 10 is a range of 5 particles. ISO code of 11 is 10, ISO code of 12 is 20, and so on. The ranges get substantially bigger the higher the particle count gets. So keep that in mind as we go through the example here. Now, if you look up in the top, you'll see an example of a particle count, and it begins with a value of 151,773 particles per milliliter that are greater than 4 microns. Well, you look over to the chart, and 151,000 and change fits somewhere between 80 and 160,000. That is an ISO code of 24. So you can see why we filled in the ISO code in that table as 24. You come down to the next particle count, and you can see where that range falls in, and it gets assigned an ISO code of 22. And you can see the last one, it falls into another range, and that is an ISO code of 19. So you can see the little lines that go across from the example to the ISO code table. Now, this simply shows you how we convert a count into a code. And I know, again, from experience, that all we did was we took one set of numbers that you had no hope of understanding, and we've converted them to a new set of numbers that you still don't really understand. Right? ISO codes are not intuitive, and they're just numbers. They don't represent pounds, they don't represent grams, they don't represent anything tangible to us. They're just a number. So how can we understand this number a little bit better? Let me show you a different example, and I think I can try and make a lot more sense out of it. Look at these 3 particle counts. Now notice how they're labeled first, second, and third sample. Now as the trend goes from the first to the second to the third sample, what would you say is happening to the particle count? Well, you'd probably notice that it's increasing. Now if I asked you, is it increasing a little bit or is it increasing substantially? That becomes a subjective answer. Right? Some of you may say, no, it's not really that much. And other people go, wow, it's almost doubling. That seems substantial to me. Right? So how can we all agree whether or not that particle count is increasing substantially or just increasing a little bit? Well, that was the purpose behind the ISO coding system. If we code these results, we level the playing field into a way that's a bit more easy to interpret. So let me show you. Using the previous table, you can look up these particle counts and you can see what code they represent. So let me show you the first sample. Right, if I look at the first sample results, it's 1,357 particles. Well, that is in the range of 1,300 to 2,500, which according to the previous table would be an ISO code of 18. So we fill in that first value as 18. Now the next result there is 361 particles per milliliter. That fits in the range of 320 to 640, which is an ISO code of 16. And the last value of 42 falls in the range between 40 and 80, which is an ISO code of 13. So we'd fill in that last one, 13. If we went to the trouble to do the next 2 samples, which I'll save us to, on time here, what you'd find is that they all code out to be 18, 16, 13. That's the issue, right? If you go through and code results and see how they all work out, all 3 of these examples work out to be 18, 16, 13. Now, if I show you that they're all 18, 16, 13 and ask you now, what is the particle count doing? From the ISO code perspective, you would say it's staying steady, right? It's not changing. It's level, however you want to phrase that. That's the point of the ISO coding system. It removes a lot of the resolution that we would look at in trying to determine 10 or 100 particle change per milliliter. We're now looking at it going, no, it's in the same range. It's in the same ballpark. So ultimately 18, 16, 13 for all 3 of these indicates that the particle count is not essentially changing that much. So now we could all agree that the particle count has not changed much. What we still struggle with is it a lot or is it a little? How clean is this 18, 16, 13? Is it really clean enough? Is it not clean enough? Where does it fit on the spectrum? So to help you understand that, I can refer to an old Caterpillar study where they took an entire drum, 55 gallons of oil, and estimated that it would only take 1/2 of a teaspoon of debris to render the particle count of the entire drum of oil at 18, 16, 13. So now you have a tangible way of addressing what does 18, 16, 13 look like. But as I said, new oil was about 20, 19, 16. So if you look at it from a perspective of ISO codes, and this is how the math gets easy, new oil being 20, 19, 16 compared to this example here being 18, 16, 13. 20 is 2 codes higher than 18. Every time the particle count goes up by 1 code, you know it doubles the number of particles, roughly speaking. If it goes up by 2 codes, it doubles again. So that is 4 times higher. So new oil is at least 4 times dirtier than what I'm showing you with this caterpillar study. So take 1/2 of a teaspoon and multiply it by 4, you end up with 2 teaspoons. It tells you there's approximately 2 teaspoons worth of material in every single drum of brand new fluid that has not been pre-filtered, right? Just taken under standard delivery conditions. So it starts to paint a picture of just how much material is actually in a drum of oil. And if you look at the rest of the ISO code, compare 20, 19, 16 to 18, 16, 13, that's 3 codes higher on the last 2 categories. So 3 codes is double it, and double it 1 more time. That's 8 times dirtier. So to appreciate 8 times dirtier, that would be about 4 teaspoons. I have a different example here for you. What if I told you that used engine oil was dirty? Right? I don't think you've learned anything new. I think you already knew that, and you probably would have said, yes, I understand it's dirty. But here's a comparison of the typical particle counts of new oil as compared to used engine oil. And used engine oil on the right, you can see is 3 codes higher in each of the categories. Being 3 codes higher, that works out to 8 times dirtier after use. So I'm just giving you a mathematical way of understanding what 8 times dirtier actually looks like. We know used engine oil is dirty. We can see it with our eyes because it is discolored. We can't necessarily see the individual particles nor necessarily feel them with our fingers, but we know in our hearts that used engine oil is in fact dirtier than new oil. But let's look at this from a different perspective. Imagine you have a hydraulic system and you ask somebody within your facility to go get you some clean new oil. So if they go out into your lube room and they took a look around and say, nah, you know what, I don't think any of these drums are that clean. Look at the way they're being stored. So they decide to go right to the warehouse. And again, they look around the warehouse and they go, I don't like the look of the way the drums are stored here either. So they talk to your warehouse manager and they ask that person, what's the freshest oil you have? They want the drum that's been stored the shortest period of time because that is the least likely to build up contaminants in it. And the warehouse manager says, you're in luck. We're actually taking delivery right now of the next shipment of oil. So you go to the back of the warehouse and lo and behold, there is your lube supplier delivering lubricants to your facility. You go up to the truck and you ask them for the next drum they remove from the truck, and lo and behold, when they give it to you, it's still warm to the touch. It's that fresh from the refinery. So I'm exaggerating, I know, but bear with me. If you take that drum of very, very fresh oil, it was just, essentially bottled at the factory, hours ago, and bring it into a controlled environment, a room within, say, the office space of your facility where it's under a filtered HVAC system, the room seems relatively clean. If you open that drum, you're still going to get 2019-16 is all I'm saying. But you want to put that oil into your hydraulic system. Well, I'll tell you this, under normal operating conditions, your hydraulic system is going to look a bit more like this. At the upper range, at its dirtiest, your hydraulic system is probably like the right-hand picture. Your new oil, on the other hand, is the left-hand picture. And if you look at the ISO codes here, we're now talking about 4 ISO codes higher. So that means there's about 16 times as much particulate before it's been used than is recommended or asked for by the OEM for the hydraulic system. So if you can appreciate whatever difference there is between new oil and used engine oil, imagine twice the difference is what it looks like, relatively speaking, of your running hydraulic fluid and you dumping in new oil that has not been pre-filtered in some way, shape, or form. So that's what I'm trying to really instill in people, is that if you don't take the measure to pre-filter your oils to at least the cleanliness of your operating system, if not maybe a little bit cleaner, every time you add oil to your system, you're shocking your system with dirty oil. Now, I'm not saying you're going to cause an immediate failure. I'm just saying you're going to tax the filters a little bit. And the point is, why tax the onboard filtration system, forcing you to maybe change those filters a bit more prematurely, when you have the ability to use offline filtration to clean that oil up significantly? So the question really becomes then, if we can appreciate 20, 19, 16, or whatever cleanliness you want to believe your new oil is at, how clean should it actually be then? So let me give you an example of how clean it should be using just a hypothetical system. So our hypothetical system looks like this. We have ourselves a variable piston pump. We have ourselves a servo valve. And somewhere else within the system, there's also some journal bearings. Now, as long as you know the system pressure, you will now have enough information to be able to determine what is my typical target cleanliness. So in this case, let's say it runs over 3,000 PSI at the maximum, somewhere within the system. So knowing this criteria, we can go forward and identify what is my target cleanliness. And this is a bit of the eye-opener for some people, because a lot of people suppose that each machine type has its own target, that you would set the target for a gearbox different than a compressor, different than a hydraulic system. And that's not always the case. What we're going to do is we're going to set the target cleanliness based on the tightest clearance within that lubricated system. And how we do that is by understanding the components that are within the system and what their target should individually be. So what we do is we use charts like this one that I got from HiPro. Now, HiPro has published this table with a list of recommended cleanlinesses for different types of machine parts at different pressures. Now, the really nice thing about this, and of course this is coming from being a filter supplier perspective, they give you filtration requirements to hit the target, which I'll address when we get to the end of our discussion here. So look up on this chart in the top table, variable piston pump. So you see it there. You can see if you scroll on over to the right, you see over 3,000 PSI, and the recommended cleanliness that it has is 16, 14, 12. Okay, hold on to that number for about 10 seconds because you're not going to need to remember it. Come down to the lower table and look up servo valve, which is the very bottom row for that system, and over 3,000 PSI, it says 15, 13, 10. Why you don't need to remember the 16, 14, 12 is because if it's clean enough for the servo valve, it's more than clean enough for the variable piston pump. So we don't care about the piston pump's guidelines. So far, what we've learned is 15, 13, 10 is the tightest tolerance. That's the tolerance for the whole system because we need to protect the servo valve. But just to make sure we cross everything off our list, let's also look at journal bearings here. And if you look up journal bearings, there's no entry for over 3,000 PSI. And if you work your way back to the left, you'll see that the entry for journal bearings is the same, whether it's high speed or low speed. And regardless, it's higher than that of even the variable piston pump. So it really doesn't become a concern to us. The servo valve being the tightest tolerance machine part, and just to show you again, 15, 13, 10 at the bottom there, sets the tone, sets the target for the whole system. And using this particular chart, like I said, it's a bit better than some of the other ones you see out there because it does have filtration requirements on it. It suggests that we need to use a 5 micron beta 1000 filter or a 3 micron beta 200 filter to achieve this particular target. And that's kind of my big point about targets. There's sort of two things you can take away from this. One is that it's a target, not a limit, which I'll address in a second. But the other one is the tightest component, the tightest clearances dictated the overall cleanliness. In this case, it was the servo valve at 15, 13, 10. So that's what is the target cleanliness for the whole system. But this will be a difficult number to achieve if we're not using at least 5 micron filtration, right? If we know our onboard filter is a 10, 12, or even worse, 20 or 25 micron filter, why should we ever set a target of 15, 13, 10? Because we'll never hit it, right? You have to keep things realistic. And that's one of the other issues that we have when people start looking into their fluid cleanliness is they start setting goals where they really are almost unachievable or will frequently be an alarm. So my point to this is make sure that you've set the target in a way that's realistic. So according to the tightest clearance component, right, you'll get that from the chart. But then look at what it says for filtration recommendations. You'll understand if that target is achievable using your current filtration setup and maybe what you might have to change. Now, if your onboard filters are only 10 or 20 microns, that's fine. but you need to consider pre-filtering the lubricant before it goes in and with a 3 or a 5 micron filter to get it down clean enough to go into the machine, and then you'll try and maintain it with your coarser system filtration. But the other issue is, like I said, not only is this difficult to achieve if you're not using it, because you can't easily get there without some help, but it's not a limit. It's a target. It's what you're trying to get to. And I always emphasize to people that you should set your limit about 2 codes higher than your target. And the reason for this is twofold. One is if you look into particle counting, you're going to find the accuracy of the test is at least plus or minus 1 code. That's right from ASTM in terms of the reproducibility of this particular test, that in particular, greater than 4 and greater than 14 micron values have over 100% variance to them, meaning the results could double, and it's considered still within range. But the other side of it is you want to give yourself, why I say 2 codes higher, is because you have 1 code as a give or take on the test. You should give yourself an additional code so you're not always in reaction mode. Give yourself some wiggle room to allow the particle count to fluctuate from sample to sample before you have to take an immediate next step to try and remedy it. So with that, hopefully the big points I've hammered home in this first module of, like I said, a series of 3 is 1, new oil is not clean oil. It's not clean enough for most systems to meet most OEM recommendations. And 2, how you set that target cleanliness is, if it's not coming straight from your OEM, you can set it yourself knowing where your tightest clearances are located. And if you don't know that off the top of your head, that's what the charts are for. They help you along that path to understand just how clean should it be. So with that, I'll conclude here. We've got several minutes here for questions. I'll turn it back over to Heather and see if anyone's submitted any. So thank you. Oh, now one question I'm seeing myself here. People ask why there's variance to the particle count, why that's allowed by ASTM. There's kind of a 2-part answer to that one, I would guess. One is that any test has an allowable variance from sample to sample, simply because, different handling, machine noise, things like this, that always allows some fluctuation in results. But the other one is, and I guess this is something not widely known unless you're familiar with the testing, is that a test like particle count actually doesn't measure the particles dimensionally in terms of like longest measurement or shortest measurement or average measurement. Both particle counting technologies that exist, one's called optical, which some people call laser, the other one being called pore blockage, each use their own techniques for essentially estimating particle size. Optical particle counting uses something called spherical equivalency. It means it assumes particles are spheres, and it sizes the particle based on the area of their shadows. So as an example, if a 10 by 1 micron particle goes by the detector, a 10 square micron shadow is created. And what this does is it then estimates what is the diameter of a circle that would create a 10 square micron shadow. And to save you the math on that one, is 3.6. So a 10 by 1 micron particle, according to optical particle counting, is determined to be 3.6 microns in size. And since optical particle counting doesn't report any values below 4 microns, that particle goes unreported. So there's an idea as to sort of the inaccuracies there are with optical particle counting, because it's not really truly measuring every particle. It's estimating its size through its own way. Pore blockage is a little bit more direct because it's using an actual calibrated screen to measure those particles. But the screen is at one dimension, either 5, 10, or 15 microns. And we measure the particles as they build up on the screen by measuring the flow decay on the opposite side of the screen. And then we extrapolate from that result the rest of the sizes of the particles. And that's based off of known calibrations. So still, it's an estimate in some ways, but at least it's a logical estimate if you want to think of it that way. So my point being, it adds variance to those particle counts, which is why you have to be a bit forgiving with particle count results. Are there any other questions, Heather? Oh, you might be on mute.
Yes, thank you. I did lose my internet connection there for a moment. So we did have a question from Jerry, and he was asking if you have found any lubricant manufacturers that restrict micron size for filtering their oils.
There are two suppliers I can think of that in any way, shape, or form address fluid cleanliness, if that's what you're getting at. One being Royal Purple, which is widely known in industry for having pre-filtered lubricants. Of course, that's always at a cost. And they will report, I won't say guarantee because that's not the word they use, but they report that their oils meet a typical cleanliness. So take that to the bank. Typical cleanliness of something in the neighborhood of 16-14-11 to 14-12-9, depending on which oils you buy from them. The other supplier would be people who are distributors of Chevron products. Chevron has an IsoClean system in place, which is not necessarily utilized by all Chevron distributors. So you have to ask about this one. But they have standards for pre-filtration of their lubricants from the distributor level. So a distributor receives the oils in bulk, and they can either put them directly into containers or they can pre-filter them into containers, and therefore they're able to give you a cleanliness of your particular fill. And of course, that is always at an upcharge too. So as to what micron value those are at, it varies a little bit, but you have to be in that range of, say, anywhere from about 3 to 10 microns, depending on your supplier, to have an effect on your particle count. As to exactly which one they use, that's a question you can ask them, because they should be able to tell you that. Or the better question is, what cleanliness are you guaranteeing it? It doesn't matter what filter they use, you want to know what target they're getting to before they package up that drum or tote and deliver it to you.
Yes. And then we have another question that is along the lines of new oil as well. And they asked, how can we ensure that new top of oil is clean without contamination? Are there any precautionary quick tests we should perform? And they say sometimes it could be due to storage of drums not being, or incorrect storage, open drums, etc.
Well, that sounds like the perfect question to give us a lead or segue into part 2 of this series, where we will talk about storage and best practices. But as to testing, really all you can do is either have your own particle counter, which they do sell portable versions of this, which use the same technology we do in the lab, or you can send a sample to the lab. What I would caution you on, and this actually works in your favor almost, is that portable or online, inline, whatever you want to call them, particle counters that people can use on site tend to report a little on the high side only because of sample preparation. Most people run their samples neat through these machines, whereas at the lab, we do a little bit of sample prep if we're going to do the same optical measurement that you would do, because we want to remove air bubbles, water molecules, and soft varnish particles from being counted as well. Now, obviously, new oil won't have soft varnish particles, but through handling, we do expect that there will be air bubbles in it, especially once we get it, because we shake them up real quick, very vigorous, and a lot of air can get in there, and we need to remove that air before we run the test ourselves. So our results typically come in a bit lower than what people will do if they do it on site. So it does work in your favor. If you can hit your target without the sample prep, then you know for a fact it's probably even cleaner than that. But like I said, unless you're going to do a particle count through some mechanism, you won't know how clean or not clean your fluids are. You can only suppose that through handling, they're getting dirtier. But how much dirtier, it will depend. So yeah, always follow up with a sample one way or the other.
Great. And then we have a question about asking if you can explain the difference between the NAS value or NAS value and ISO 4406.
Yeah, there's an easy answer to that, and there's a longer answer to that. The easy answer is there's no comparison almost. The longer answer is an ISO code is determined by a particle count done per milliliter, and NAS is done per 100 milliliters. So right away, understand the values are going to be about 100 times higher when you look at the actual counts. But NAS uses a class system rather than a code system. And the difference being primarily that ISO uses what we call a cumulative count, meaning that each count, as you get smaller and smaller, is successively higher. right? Because you're accumulating the particles from greater than 14 into the greater than 6 category, and from those two categories into the greater than 4 category. And NAS uses what we call a differential count, which means each count is its own range, and they range from 5 to 15 microns, 15 to 25, 25 to 50, 50 to 100, and then simply greater than 100. So the reporting is significantly different. Like I said, the numbers are about 100 times higher. They're done in ranges, which means the values actually get substantially smaller as you get into larger particles. And then the numbers they assign, instead of being ISO codes, are NAS classes. So to try and compare from one to the other is not an easy task, and most of the online sort of converters or calculators that you can see where you just plug in your ISO code and it tells you what NAS is equivalent to are incorrect. If you want to see a true NAS, simply ask the lab doing the measurement to report it NAS. It's literally a button that we press on the machine to toggle between reporting styles. We don't have to do anything different for the testing. We just get it to report, and it reports it based on the actual measurements, not a conversion. And the only other caution I'll give you with NAS, because it's an archaic system, but some people do still use it. NAS is always reported either individually per range, so your 5 to 15 gets its own class, 15 to 25 its own class, so on and so forth, and you just go by the highest class, or it's reported as a single class for the whole particle count, and what that is simply which one was the highest. So if you have a target like, say, NAS 7, and you get the results back from the lab and it's NAS 8, and therefore you know it's a fail, what you really want to dig into is which range failed. Was it the 5 to 15? Because that could be really tricky trying to get the oil clean enough to meet that target. Or was it the greater than 100, which means maybe it took just one single particle at that range to end up as a class 8, and you can easily clean it up and get it into range. So I like to see NAS results reported all the classes for each range, just so I have an idea exactly why the particle count is or is not meeting the spec versus the single code way, which, like I said, doesn't give you the proper guidance. There you go.
That was the long answer. It looks like we, yes, we have another question that just came in, and they're asking, how would you address a customer who is concerned about over-filtering or filtering out their additives?
Oh, I like that question.
That's a loaded question.
We're going to run out of time, but anyways, here's the long,
yes.
answer. So, give you the backstory first. Full disclosure, as Heather said, I'm editor of TLT magazine for STLE. And what that means is I write a monthly column. I get 700 words. I can write whatever I want. This topic was something I wanted to write about because it bothers me. It bothers me because there's a lot of misinformation out there. So I knew I couldn't write this article. I couldn't fit it into 700 words. So I had lunch one day with a friend of mine, Dr. Neil Cantor. He's one of the other writers for the magazine, and he often writes feature articles. So I said, Neil, you got to write this one for me. Answer the question, can you filter out additives? Now, Neil deals with a lot of lubricant suppliers and additive companies, so he's got a lot of contacts he can talk to at these companies. Many years ago, I used to be a research scientist for a filter company, so I had some filtration contacts, and I supplied those to Neil. So he compiled a list of 16 individuals to interview for this article to ask that question and get this answer I'm about to give you. When he interviewed the 16 people, they were mostly happy to answer the majority of his questions until he came to that burning question: will filtration remove additives? Now, if you want to believe in conspiracy theories, go ahead, because 10 people backed out of the article at that point. They all said, we're not answering that question. Now, of the 6 who said they would, 5 of them said they would only do it under condition of anonymity, meaning we could not mention their name nor their company name. So now the article starts to, not carry the weight that you would hope that it would. And there's one poor guy who's willing to go on the record. Well, it's not fair to out him, so he's also listed as anonymous. Now, when Neil wrote this 6-page article addressing this, and he covered it from a variety of angles, so here's your unequivocal answer. The answer is no. You cannot filter out additives. The direct quote from the magazine article says, filtration studies on both new and used lubricants of several base stocks, so we're trying to be as inclusive as possible, show that no additives were removed after hundreds of passes. To save you reading the whole article, they used 1.2 and 3 micron filters for this study. So when Neil wrote this, how we write articles for TLT is once the article is written, it has to go back to the interview sources so they can vet it. So they can say, yes, that's what I said. Yes, I like the way you phrase this. I don't look like I'm being taken out of context or my facts are being misconstrued. My point is that essentially 16 people signed off on this article as it was written, even if they didn't contribute to the direct statement. This is as close to peer-reviewed as you can get, is what I'm trying to drive home with the long story version of this. However, saying all that, the one guy who was willing to go on the record happens to be a friend of mine, and English isn't his first language. And so he said to me, but Evan, you can filter out used additives. And I knew where he was going with this. I said, I don't like the word used because used implies not new. And what does that mean? As soon as the lubricant is being used, the additives come out? No. I changed the word to spent because there is reason, and this is understandable to know your additive. To take something like a dispersant. A dispersant is meant to bond with dirt particles to prevent them from sticking to each other. If the dispersant is attached to the dirt particle and you filter out the dirt particle, did you technically filter out the additive? But was the additive going to do you any good later? No. So it doesn't really matter. So long story, no. The additives, short version, no. Well, can under certain circumstances, but you're filtering out spent additives that have already done their job. So no, there's no worry about overfiltration of either new or used lubricants using beta 1000 1 micron filters. Don't worry about it. You're okay. Don't believe when people tell you that you're stripping additives by filtration. It's not true. And I can send links to the complete article with the quotes. It's something I do quite frequently.
Evan, you are breaking up a little bit with the audio. It's a little difficult to hear what you are saying. But if you wouldn't mind providing me that link, I can include that when I send out the recording of the webinar so that people can reference that article.
Yeah, will do.
Perfect. And we have made it to the end of the hour. We do have a few more questions, but I will provide those to Evan so he can email people directly to continue answering those. If you do have any other questions outside of this or you think of something a week later, please keep Evan's email address on hand. You are always more than welcome to contact him or myself for assistance. But thank you very much, Evan, for your knowledge and your time. It was great.
All right, thank you.